Section 11.10 Taylor series. This is the last section we will cover from chapter 11. Now the Taylor series is actually a power series, and we write it like this. So this power series uses derivatives. It is expected that the function f is differentiable, has all the derivatives up to whatever the power of the derivative is we can take. And so the series is, so if you recall, in the power series we have summation Cn and then x minus a to the n. So here the Cn's are this kind of constants or coefficients, that they are derivatives of the function evaluated at the number a or x value a and then divided by n factorial. And this x minus a is the usual term that comes with the power series evaluated at a. So it says this power series over here with the summation notation. It is saying n goes through 0 to infinity f, and then in parentheses I have this number n, f n a. This n is not the power, it is the derivative, okay, the nth derivative. So nth derivative of f evaluated at a divided by n factorial, and then x minus a raised to the power n. So when n is 0, so we will have f 0 derivative and evaluated at a and then divided by 0 factorial and then x minus a raised to the power 0. Now the 0 derivative means no derivative, which means f of a. Just we plug in a in the function. So the first term and then 0 factorial is 1. So this quantity just gives me f of a. X minus a to the 0 is 1. So we just get the f of a. So this is the first value. Plus now second value will have n is equal to 1. So the first derivative at a divided by 1 factorial, but 1 factorial is 1. So we have f prime a x minus a. Next n is 2. So f double prime a means the second derivative evaluated at a and then divided by 2 factorial x minus a whole square. Plus now as the we are writing higher and higher derivatives, we cannot use these primes. Like f, if I have the 10th derivative, I cannot be putting 10 primes here and counting and not being sure how many there are and confusion creating. So what we do is we put a number but in parentheses. Why in parentheses? The reason is if usually when you put a number like this, that is the power. That denotes the power on the function or number, whatever. But here, because we are not yet taking the power, we are taking the derivative. So this is a symbol you might recall from Calc 1. This is the notation. So this term is that third derivative evaluated at a divided by 3 factorial x minus a to the third, and so on. We should be able to figure out the rest of the term. Now fn, this in the parentheses, this is the nth derivative of f of x, and fn a will be the nth derivative evaluated at x is equal to a. So how do we find this nth derivative? That is the question. So you will see when we do examples, then you will understand. So notes here, some things to note, that the power series this, and the function f of x have the same higher derivatives at x is equal to a. So all the derivatives of the series and the derivative of the function, they are the same thing. So in other words, if you think of this as c0 plus c1 x minus a plus c2 x minus a whole square plus dot dot dot. So then this will be the series y equal to this, and then f of x is, f of x has the derivatives. So the first derivative of the series will be y1, y is equal to, y prime will be equal to a1 plus c2 2 times x minus a and plus dot dot dot. So now we can say that this is the same as this. So that's how we are getting these f primes in here. Yeah, you don't have to worry about that. You just remember that this is the case that the derivatives of the function and the derivative of the series, they are the same everywhere at a. So when we write this series and we say that f of x is equal to this series, actually this is true only in the interval of convergence. When x is in the interval of convergence, then we can write the function equal to the series. Now if the interval of convergence is the whole real line, then of course this is true for the whole real line for any value of x. Now you might have heard Maclaurin series. So Maclaurin series is same as the Taylor series, but at a is equal to 0. So usually most of the time we will be working with the Maclaurin series or evaluating Maclaurin series because it's easier, less work and more understanding. But Taylor series, once in a while we will calculate that. But it's basically the Taylor series but evaluated at 0. So the Maclaurin series becomes summation n is equal to 0 to infinity f and derivative evaluated at 0, and we have just x to the n, not we don't write it x minus 0. So it will be f of 0 plus f prime of 0 x plus f double prime of 0 over 2 factorial x square plus dot dot dot. So let's start with the example immediately. So we have our, this is the way I have down here written the steps of finding the Maclaurin or the Taylor series. So what we do is we start with the function. So the function is e to the x, and a here is 0 because we are evaluating Maclaurin series. So what you are supposed to do is find some derivative. We cannot, of course, find all the derivatives because they are going to infinity, so we cannot get there. So, but the nice thing about e to the x, is that the derivative is itself, function itself. So all the derivatives are going to be the same in this case. So how many we want to find, that's up to you. Okay. Now I will evaluate them at 0. So usually, normally I would do this. So this and just evaluate them in front of each value. So f of 0 will be e to the 0, which is 1. F prime of 0 will be again be 1. So you can see all of these are going to be 1. F of 3 equals at 0 equals 1. So now we plug it in here. So e to the x is equal to 1. F of 0 was 1 plus f prime of 0, which is 1 again, but then it is being multiplied by x. So we have x plus, now f double prime of 0 is 1, number 2 factorial x squared plus 1 over 3 factorial x cubed plus, and now can you see a pattern here? So it will be 1 over 4 factorial x to the 4th plus dot dot dot. So nth term, if you want you can write it up here, that is some the term which has n, so if I have 1 over n factorial x to the n plus dot dot. So now we put it in summation form. So n goes from 0 to infinity. So this nth term is actually basically is going to come in here. We get 1 over n factorial x to the n. So this is the Maclaurin series in the closed form for e to the x. Okay, now we can also talk about the convergence of the series, but for that convergence we have to use a ratio test. So what is the ratio test? If you recall, so our an equal to 1 over n factorial x to the n. So an plus 1 will be 1 over n plus 1 factorial x to the n plus 1. Ratio test. L equals limit n goes to infinity of an plus 1 over an. So L will be equal to limit n goes to infinity of an. So an plus 1, sorry, is 1 over n plus 1 factorial x to the n plus 1 divided by the an, which means multiplied by n factorial over x to the n, absolute value, which is limit n goes to infinity. You know how we do it. The n plus 1 factorial is bigger, so we will open this one. So we will be left with n plus 1 times n factorial. N factorial will get cancelled with that. So I will have just n plus 1 left at the bottom and then x on the top. When we take the limit, this limit goes to 0. So what does that mean? It means that no matter what the x value of x you have, it is always going to converge. So in this case, the interval of convergence okay. So note here that in order to find the Maclaurin series or Taylor series, what we do, we start by taking the derivatives of the function. How many derivatives? That depends on when you see a pattern. Until a pattern emerges, then you should keep taking the derivative. Then similarly, once you have the derivative, then you plug in the point in there. If it's 0 or 1 or whatever is, you plug in. And again, you keep doing until you see a pattern there. And now from the pattern, you have to figure out what the formula is for the nth term. Then you have to write the Taylor series and simplify if needed. And then find the interval of convergence and radius of convergence. Usually, if the question asks now here, the question asked find the interval and the radius of convergence, so I did. But if it doesn't ask, then we don't have to. Note here to find the pattern, it is important that you do not simplify the derivatives. What I mean is that, for example, if you have something like, it's not going to be as simple as that, but if you have, okay, maybe like 1 over x plus 1, your function is 1 over x plus 1. So you can write it as x plus 1 to the negative 1. So you can see that f prime of x will be negative 1 into x plus 1 raised to the negative 2. So don't write it like negative 1 over x plus 1 yet. Okay, keep it that way. Then so you second derivative negative 1 into negative 2 x plus 1 to the negative 3. So what I mean is that do not multiply these two numbers and write it as 2 over x plus 1 whole cube. Don't do that. Keep it as it is and take the second derivative, and once we write the nth term, then we will combine later on. Okay, so let's see, look at this example. It says find the Maclaurin series for sine of x. Now when it says find the Maclaurin series for sine of x or any function, you know that x, we are doing it at a is equal to 0. So we are finding the Maclaurin series at x is equal to 0. So first I write the function. So notice here, now this is the same as the first. So now these will start repeating. So fifth derivative of f is the same as the first derivative. And so on. So now we evaluate at 0. So notice here, every even derivative is coming out to be 0. So you notice that every odd derivative we have, but the even derivative is giving us 0. So this is for when one first derivative, third, fifth, seventh, so on. But when we put it in the notation form, and it goes from 0 to infinity, or n could go from 1 to infinity. But we have to give n each like 1, 2, 3, 4. N will take on values 1, 2, 3, 4. But in this case, it's not going to work. Okay? The reason is because we are getting some of these are zeros. So maybe we should start writing the load terms. First will be f of 0 plus f prime of 0 x plus f double prime of 0 over 2 factorial into x square plus f third derivative at 0 over 3 factorial x cubed plus f fourth derivative at 0 over 4 factorial to x to the 4n plus 1. So notice here, this is gone, 0, this is 0, this is 0. So what does that tell us? That we can write only f prime of 0 x plus this term f prime third derivative of 0 over 3 factorial x to the third plus f seventh derivative fifth derivative over 5 factorial plus x to the 5 plus 7th factorial, 7th derivative over 7 factorial, and then x to the 7 and plus dot dot dot. So when we want to put it in the compact form, we have to check. But first let's put the value. So f prime of 0 was 1, so I get x. F third derivative of f, we had negative. I get negative 1 over 3 factorial x to the third plus, so remember f fifth derivative evaluated at 0 gave us 1, so we get plus 1 over 5 factorial x to the 5. So can you see now the pattern? So we are going to get next one is 1 over 7 factorial x to the 7, then sorry, this will be negative, next will be now positive. Now I didn't evaluate that, but I know this is going to be the next term. The next will be negative, but then, so you can just, usually I would go up to write the term which has negative sign and with a plus sign, then dot dot. That's, so we could stop here and put plus dot dot dot, or you can do one more term, 1 over 11 factorial x to the 11 plus dot dot dot. So now we can put it in compact form. Now notice again, n goes from, I should not be putting 0, I will be putting a 1 to infinity. And what do I put here? So we have x to some power and 1 over some factorial. So how do we do it? Well, 3, 5, 7, 9, these are odd numbers. So odd numbers are denoted by 2n plus 1. And the even, this is odd, even is denoted by 2n. Now n is an integer, n will go 1, 2, 3, 4, 5, or 0, 1, 2, 3, 4, 5. So, but if I just put n here, then I will get the even powers as well. I don't have even powers in my series. So I will put this as 2n plus 1. And same thing here, 2n plus 1 factorial. So that is our, by the way, so there is a alternate negative sign, so there will be a negative 1 to the power what? Now here we can have n, we don't have to have the 2n plus 1. But again now, let's see. Maybe I think we need to have it from 0. The reason is because when you have 0, then first term will be positive, and when you have 0, n is equal to 0 here, then you can have the, you'll have the x to the 1, which is the first term here. If we do it with x is n equal to 1 to infinity, then we can have this as n. Here we should have n plus 1. Oh, no, n was okay. Then if I do start with n is equal to 1 to infinity, then I will have to do n plus 1, and then what about this one? If I do 2n plus 1 and my first value is 1 for n, then I end up getting a 3. So I will miss some terms. So then I will put 2n minus 1. So 2n plus 1, 2n plus 3, 2n plus 5, all these are odd numbers. And you can go on the other side, 2n minus 1, 2n minus 3, 2n minus so on. So which number you need, you just use that. So divided by 2n minus 1 factorial. So this is how you find the power series, the Taylor or the Maclaurin series for functions. Okay, now you can imagine there will be a Maclaurin series for cosine x. So you guys should try that on your own and see what you get. So here we got, I showed you two series. Let me write them over here. E to the x is 1 plus x by, and these are something you, at least e to the x is something that you can memorize, or you will have it memorized. X squared over 2 factorial plus x cubed over 3 factorial plus x4 over 4 factorial plus 4 and sine x cosine x. So let's look at one more example here. Find the Taylor series of x is equal to ln of x at x is equal to 1. Now note here, I cannot find that x is equal to 0 because ln of 0 is not defined. So if I had the function ln of x plus 1, then we could do it at x is equal to 0, but not in this case. So we are doing it at so f of x is equal to ln of x. So what I do, I start taking derivatives. F prime of x will be 1 over x, which I can write as x to the negative 1. F double prime x will be negative 1 x to the negative 2. Again, if you want, you may write it like this, but for the derivative, we need to use this term. derivative of negative 1, negative 2, x to the negative 3. Maybe you can recognize the pattern already. So now this will be negative 1, negative 2, negative 3, x to the negative 4. Okay, I think these are enough. And now we evaluate ln of 1, which is 0. 1 over, sorry, prime of 1. So 1 will be just 1. And I get what? Negative 1. I will have negative 1 times negative 2. So if you note now, so we can simplify here now. This can be written as negative 1 raised to 2 times what? 1 into 2, which is 2 factorial. This can be written as negative 1 to the third, and then 1 into 2 into 3, which is 3 factorial. And then same thing, next will be negative 1 to the 4, 4 factorial. And you should be able to see how the terms will go. So the nth term, so fn 1 at 1 will be what? From this category or this pattern, we have negative 1 raised to. So notice here, when we have the fourth derivative, so n is 4, I am getting a 3 factorial. So 1 less, and similarly, the power on negative 1 is 1 less than the number on the factorial. So this will be n minus 1, and then n minus 1 factorial. So which means, or we could say, or you could do n plus 1 derivative of n, and then this will be now negative 1 raised to the power n times n factorial. For that, in the summation notation, ln of x we will have a negative 1 raised to the power. Again, now it depends on which value you want to write. I think first we have to write the expanded or the open form. Ln of x going to be f of 1 plus f prime of 1 x plus f double prime of 1 over 2 factorial. Oh, sorry. See, this is what happens with the Taylor series and not at 0. We are so used to doing the Maclaurin series that we forget. Now we are doing it at 1, so we have to multiply by the factor x minus 1. So it will be f of 1. So this is going to happen when n is maybe 0 plus, so we are not putting the x minus 1. The first derivative will be x minus 1 plus second derivative divided by 2 factorial x minus 1 raised to the power 2 plus third derivative valued at 1 divided by 3 factorial and x minus 1 raised to the power third and then plus 1. So this gives me f of 1 was 0. So this is 0, we don't need that. So f prime of 1. F prime of 1 was 1. I have 1 into x minus 1 plus f double prime of 1 was negative 1. So the next term will be negative minus 1 over 2 factorial x minus 1 whole squared plus, so f3 was negative 1 whole square into 2 factorial. Plus minus, the next one is negative 3 factorial divided by 4 factorial times x minus 1 raised to the power 4 plus minus, next one will be negative. So now we try to put it in complex form. So it will be summation n is equal to 0 to infinity. We'll see in a minute, do we want 0 or do we want 1? Okay. So I have negative 1 raised to some power. I will see what it is. I know I'm going to get an x minus 1. Actually, we needed to simplify it a little bit more here because it can be simplified. So first term is x minus 1 plus x minus 1 whole square over 2. 2 factorial is 2. Now this one, 2 factorial over 3 factorial becomes simpler. This becomes 1 over 3. The bottom can be written as 3 into 2 factorial. So 2 factorial, 2 factorial cancels out. So I get plus 1 over 3 factorial or x minus 1 whole cube over 3. Next is negative. Now same thing, 3 factorial over 4 factorial gives me 4 at the bottom. And I have x minus 1 over 4. Next will be, now you see the pattern, x minus 1 to the 5th over 5 minus x minus 1 to the 6th over 6 and then so on. So putting it in the compact form, summation, we have a negative 1 and it is going to go from 1 to infinity. So the power here is 1. So negative 1 raised to some power. So if I say 1 n, so then n, the first value n will take is 1. So it will give me first term as negative, which shouldn't happen. I have to add 1 or subtract 1. Then I have x minus 1 raised to the power n, because it goes like that. So the first term is has an x minus 1 as power 1, and we get x minus 1. When we have n is equal to 2, the power goes 2 and the negative sign power becomes 3, so we get a negative sign. And so this whole divided by, or you can say this thing, you can put the bottom in under one of these, or you can put it under the whole thing. It's your choice. Or I could put it here, or I could have put it here. So that is how we write the series. Okay, I'll stop here and come back to do more in the next video.